Hey guys, welcome back to chapter 14. Today we're going to introduce this idea of pH. So in the previous problem, we looked at something like this, okay? So we determined the hydronium concentration given the hydroxide concentration. We did that by using the ion dissociation constant, Kw. But I posed this question at the end of the video. What does that even mean? So I would be able to look at hydronium concentration as 4.0 times 10 to the negative 6 and have any indication of what that means, right? And when we talk about things like pools having a correct pH, when we talk about things like water being alkaline, we don't talk about the concentration of hydronium and hydroxide. What do we talk about? We talk about pH. So I really think, this is a personal opinion, I really think pH came about because nobody likes exponents, right? So how can we make these numbers a little bit more user-friendly and something that actually means something to us? So pH is defined as taking the negative log of the hydronium ion concentration. So if we know, or if we're given the hydronium ion concentration, we can simply type into our calculators negative log and then type the number. So let's do that. So negative log of 4.0 times 10 to the negative 6. When we hit equals, we get a number that is much more user-friendly. We get 5.38. Now, a pH of 5.38 is not only more user-friendly, it's a relatively easy number to deal with, but it also means something to me. That's a pretty low pH. I know it's going to have some acidic value to it. So here's your introduction to the pH scale. The pH scale tends to run from 0 to 14. Technically, there can have a negative pH. Technically, we can have a pH over 14. It just doesn't exist often, okay? But something that is on the lower end of the pH scale would be more acidic. So something with a pH of 5 is acidic. Something with a pH of 1 is very acidic. Something on the higher end of the pH scale is more basic or alkaline, right? So again, something with a pH of 9, pretty basic. Something with a pH of 14, very basic. And then our middle of the scale is 7. Something that has a pH of 7 would be considered neutral. So how are we going to see this? Well, we're going to see pH in a variety of problems. It's going to get a little bit more complex in the second half. But let's see our first introduction at a pH problem. So determine the pH of a solution that has a hydronium concentration of 1.8 times 10 to the negative 4th. So this is going to be just kind of a basic plug and chug problem. So the formula for pH is negative log of hydronium concentration. So we're going to take negative log of 1.8 times 10 to the negative 4th. And we get that pH equals, let me type this in my calculator, negative log of 1.8 times 10 to the negative 4th. And we get 3.7. Ooh, not over there. 3.74. So very quickly, we can take a number that doesn't really mean much to me, 1.8 times 10 to the negative 4th, throw it into our calculator, and I get a pH of 3.74. Something else that also exists, just not as widely used, is the pOH scale. So pOH is defined as the negative log of the hydroxide concentration, okay? Sometimes we solve problems and we know the hydroxide concentration, Well, we can make that number a little bit more user-friendly as well by taking the negative log of it. The pOH scale is the inverse of the pH. So something that has a higher pOH means it's more acidic. So a pOH of 13 means it's very acidic. Something that's lower on the pOH scale is more basic. So pOH equals 2, that's basic. The one thing that is the same is the pH. Now that we understand what pH and pOH are, how they're calculated, there's some really intriguing relationships that we need to keep our eye on. So practice with these relationships in this first half, because in the second half of the chapter, these relationships are going to be very important when trying to solve these problems. But here's some just helpful, useful relationships. So the first one is that pH plus pOH will equal 14. Okay. Why would this be important? Well, down the road, we may solve for hydroxide concentration. Then we solve for pOH, and through simple arithmetic, we can get to pH. So this is a relationship that's very useful. This stems from the relationship that we've already seen. So it's derived from this idea that the hydroxide concentration times the hydronium concentration is that 1.0 times 10 to the negative 14. So it's derived from that relationship. So just kind of don't forget about that relationship as well. That's going to be useful. We will see this guy in the second half of the chapter, so for the next module. But if we're talking about pH, pOH, we're going to go ahead and talk about pKa. So pKa, again, is just taking the negative log, just like we did for pH. But we're taking the negative log of that equilibrium constant K. There's that relationship. So let's take a look at an example utilizing some of these helpful relationships. So I'm asking you to determine the pH of a solution that has a hydroxide concentration of 2.5 times 10 to the negative 9. Go ahead and pause the video and see if you can solve it. I'll catch up to you in just a moment. All right, so there's two paths to solving this, and both paths are correct, but I do want to at least show you those paths. So the first path, likely the one you guys took, is we could get to pOH and then to pH. Okay. So to get to pOH, we take the negative log of the hydroxide concentration, since that's what we're given. So negative log of 2.5 times 10 to the negative 9th. And we get that the pOH equals, type it in, so we get pOH is 8.0, nope, 8.60. Then we use the relationship that pH plus pOH equals 14. So pH equals 14 minus 8.60. And we get that pH equals 5.4. So I suspect this is probably the path most of you took, but I do want to at least introduce this idea that there is another way to solve this, okay? So if we wanted to, we could use the relationship that the hydroxide concentration times the hydronium concentration equals that 1.0 times 10 to the negative 14th. So we could plug in the hydroxide concentration. Keep this hydronium, so solve for hydronium. So I'm going to get hydronium by itself, so divide by 2.5 times 10 to the negative 9th. Those cancel. Whatever I do to the left side, I also have to do to the right side. And I get the hydronium concentration is, let me type this in, 1.0 times 10 to the negative 14th divided by 2.5 times 10 to the negative 9th. And I get that this is 4.0 times 10 to the negative 6. And then I can type this into my pH equation. So take the negative log of this, and we get same answer. I get 5.39, but 5.4, 5.39, same thing. Okay. So what you'll see is there's going to be multiple paths to solving these problems. One is not more right or wrong than the other. It's just what path your brain sees, and just take that path and math it out. I hope you guys found this helpful.